I'm pretty sure looking at it, there was, I mean, just in seeing how young everyone's faces, I expect probably that I'll be asking the same questions come next day of class. So let's recall where we were last time. So we were in the midst of the proof of the extreme value theorem, and we had gotten kind of sidetracked on this concept of compactness. So if you recall, the extreme value theorem says that if I is a closed bounded interval and f is a continuous function on I, then the supremum and the infimum of the image of f over the set I are both in the image of f over the set I. So that was the big theorem. And where we got sidetracked chasing down is this word compactness. Compact sets are generally denoted with K or C for compact. So what two adjectives do we need a set to satisfy to call it compact? Bounded and closed. Well, what does closed mean? Closed means K contains its limits. And we got a reformulation of, well, so one important thing we saw about compact sets. We saw that closed bounded intervals are compact, which they better be because in their very name they've got the word closed and bounded. And then we developed a slight reformulation about the word compactness, something very sequential. Every sequence of elements of X sub n has a subsequence which converges to an element of K. And maybe let's just get the references correct because I'm going to refer to these an awful lot today. So, AB is compact is the content of theorem 3.3.5. Theorem 3.6 is sequential compactness. So those are the two tools that we'll use today. So let's talk about proving the extreme value theorem really over any compact set. So here it is. Let's let K a subset of R be compact, and f from K to R be a continuous function. Step one is to prove that the image of that function is also compact. So let's see, there are one or two different ways we could proceed. We could either say, well, one way we could do this is by considering any closed bounded set and a continuous function on that set and showing that its image is closed and bounded. But that'll actually wind up being kind of challenging, because it certainly isn't the case that a continuous function applied to a closed set will be closed, or a continuous function on a bounded set must be bounded. Right? Think about like 1 over x. that sends the open interval from 0 to 1, which is definitely bounded to the interval from 1 to infinity. So boundedness won't be resolved on its own, neither will closedness. So things will be hurt if we try to do that. Instead, let's use this reformulation of sequential compactness. Let's show that for every sequence of elements of f of k, there is a subsequence which converges to an element of f of k. Let's do that. So, we must show that k is compact by this sequential compactness theorem. We must show that for every sequence of elements of f of k, there exists a convergent subsequence with limit in f of k. Right, if we could show that, then we would know that this thing is, that f of k is compact. Cool. Well, but now this is like here's what we need to show, and that statement contains the first line of the proof. I need to show something is true about every sequence of elements of f of k. So what should my first line be? Consider any sequence of elements of f of k. I'll use the letter y sub n for this sequence because f of a thing is often called y. Like these are things in the image, so they should be called y. Let's let yn be a sequence of elements of f of k. I need to show that y sub n has a convergent subsequence whose limit is in f of k. So I need to show that there exists a subsequence y sub n sub k with limit of y sub n sub k in f of the set big K. Cool. So there's what I need to prove. And here's how I'll try to do this. I'll go from the sequence of elements of f of k to a sequence of elements of k. But I know that k is compact. So I can use compactness for k downstairs to prove something upstairs, to prove something about the set f of k. So let's try to do that. So each of these y sub n's is in f of k. Maybe it would be nice to have that quantified. Oops. I'll fix that later. For any natural number n, y sub n is in f of k. Who remembers the definition of the set f of k? What does that set mean? Well, I guess the better question is, what does it mean to say y sub n is in f of k? There's something in the domain, there's something in K which maps to y sub n. I may as well call that thing x sub n. So there must exist something in the domain, I'll call it x sub n, such that f of x sub n equals y sub n. Now, as you said, x sub n, the sub n is because it depends on n, because for different n's I get different y sub n's. For different y sub n's I'll get different x sub n's. Does this result in a sequence of elements of k? Yeah. Each of those x sub n's is in k. This is a sequence of elements of k. I know that k is compact. Wow, well, that was one of the blanks. So, by sequential compactness, what can I conclude? So this is the theorem I'm referring to as sequential compactness. So the set K is compact. And compactness is equivalent to this second thing. So I know for a fact that for absolutely every sequence of elements of K, there exists a convergent subsequence with limit in K. So what can I conclude about the sequence X sub n?
There exists an X sub n sub K.
Yeah, that converges, and even better, converges to an element of K. So by sequential compactness, I see that. Do I give myself space? I do, but I'm going to put it here anyway. We see that there exists a subsequence, X sub n sub K, such that the limit of X sub n sub K exists, and even better, that limit is in K. People feel pretty good? Good. Okay, so let's let X sub n sub K be that sequence of elements. It's given that name in the previous line. And let X, which is in K by assumption, by the previous line, be its limit. So that means this X is in K, is in the domain of F. So it makes sense to talk about F of X. So here's what I'm going to try to do. I'll try to show that the same subsequence, y sub n sub k, converges to f of x. Will that complete the proof of the theorem? Because this will be a subsequence of y sub n, which converges, and f of x, well, x is in k, so that's something that's in f of k. So let's try to do it. So let's try to analyze it this way. So f of x, what is x by definition right now? Limit of x sub n sub k. So let's see, this number of x, it's in the domain of f. Is this function continuous at that point x? So we can use sequential continuity, which says that f of the limit of f of x sub n sub k must be the same thing as f of the limit of x sub n sub k. So tell me, what is f of the limit of x sub n sub k the same as? Yeah. Aha, so now I see f of x sub n sub k. I already have a name for that though. What's f of x sub n sub k the same as? Y sub n sub k. Okay, those boxes should have been bigger when I typed them. Because f of x sub something is exactly the same as y sub something. That's how we chose the x's. Wait, did this just achieve everything we needed? Yeah, nice. Okay, cool. So we have a subsequence, y sub n sub k of y sub n, which converges to f of x, which by the very definition of image is in f of k. So let's just summarize what we've done. We have proven, we showed, that for every sequence y sub n of elements of f of k, there exists a subsequence y sub n sub k which converges, let's be more efficient with our space, which converges to an element of f of k with limit of y sub n sub k in f of k. So, by sequential compactness, which happily I wrote down the number corresponding to, That is to say, theorem 3.3.6, f of k is compact. Nice. People have any questions about how that proof went? And so now, what could you try to do? You could try to like another approach to this proof could be doing it right from definition. But that might be hard. If you wanted to prove that the sequence is bounded, that the set f of k is bounded. When you want to try to prove that, you would use both boundedness and closedness when you try to do it. So there's going to be some difficulty. So let's, step 2. So we now know that the image of a continuous function on a compact set is compact. So in particular, that means f of a comma b, brackets, is compact. That's nice. That's something. As our next step, let's prove that every compact set contains its supremum and contains its infimum. All right, and that'll will be done. I'll then be able to prove the extreme value theorem by just saying appeal to that theorem, appeal to this theorem, we're done. I think so. Let's do it. So let's let K be a compact non-empty set. Yeah, I guess it better be non-empty, otherwise those won't exist. Right? Empty sets don't have a supremum because their supremum should be like minus infinity. So let's let K be a compact non-empty set. I'll prove that the supremum of K is in K. The proof for the infimum is the same, and it might be one of the homework problems. I don't know how many times I did that on this particular homework. Let's let K be a compact non-empty set. I'll prove that sup of K is in K. Let's start with this. Let's start by justifying that the supremum even exists. What types of sets have suprema? Bounded sets. Non-empty bounded sets. So my assumption, this set K is non-empty, and it's bounded. And so it has a supremum. Maybe I wanted to put those two different ones in two different things, but I think this one. So the supremum exists. Let's let S be the supremum of K, just so I don't have to write the supremum of K quite so many times. And I'll try to prove that this S is in K. So here's how I'll do it. I've already used boundedness. Let's use closedness. Let's prove that the supremum, if it's not in K, let's prove that it is a limit point in K, because then I'll get the contradiction of closedness that I need. And in order to get that result, let's even just remember the reformulation of supremum in terms of epsilons. So let's let X a subset R be non-empty. Let S in R be an upper bound for X. Then S is the supremum if and only if what happens?
And you said X approximate S. I don't know how that works in terms of epsilon.
Yeah. I mean, for every epsilon bigger than 0, there is something in the set that's that close to the supremum. More precisely, let's say it this way. For all epsilon bigger than 0, I'm going to give myself some space. S minus epsilon. Could S minus epsilon possibly be an upper bound on the set X? If S is the supremum? No, because then S would not be the least upper bound. What does it mean to not be an upper bound?
There's some element greater than.
There's some element in the set that's greater than it. And the next bit isn't actually part of the theorem, but could X possibly be bigger than S? No, because S is just an upper bound. So I'll put this in a different color because it's not actually part of the theorem, but cool. So let's appeal to sequences all over the place. So I'm going to try to come up with a sequence of elements of K that converges to the supremum. Because then by sequential compactness, I'll know that the supremum is actually in the set. So let's take epsilon n to be your favorite sequence of elements that converge to 0. What's your favorite sequence of positive numbers that converges to 0? Why not? Maybe you want to use 2 to the negative n because you want faster convergence, but I don't care. So let's take epsilon n to be 1 over n. Is that number positive? Yeah. So it follows then that there should be something in the set, not x, but k, such that this inequality holds for that epsilon. So there exists some x sub n in k, such that s minus 1 over n is less than x sub n is less than or equal to the supremum. As n goes to infinity, what does this converge to? As n goes to infinity, what does this converge to? So as n goes to infinity, what does this converge to? So by the squeeze theorem, limit of x sub n is equal to s. But now, this xn is a sequence of elements of this compact set K. So, by sequential compactness, is that really? This is wrong. I'll need to look into why that's wrong. By sequential compactness, this sequence should have a convergent subsequence which converges to an element of K. X sub n has a subsequence, x sub n sub k, such that limit of x sub n sub k is in the set big K. So let's maybe even just talk ourselves through why this means we're done. So I know that the limit of this subsequence x sub n sub k is in big K. But you already know what the limit of x sub n sub k is. What must the limit of x sub n sub k be? S. Because it's the subsequence of a sequence what converges to S. So that means S is in K, which is all we wanted. So the theorem is that the proof is basically done. We just need to wrap it up. So as x converges to S, x sub n sub k must also converge to S. But I've already said that limit of x sub n sub k is in K, so that means that S, the supremum of K, is in K, and that's all we need. Do you think the proof for the in theorem will be basically the same? Yeah. Maybe I'll wind up thinking about an inequality that looks like inf minus x, inf is less than or equal to x is less than or equal to inf plus epsilon instead. But otherwise it'll be like the exact same argument. So that completes the proof of that. And now let's prove the main theorem. Let's prove the extreme value theorem. Let's prove that if I is a closed bounded interval on f defined on I is continuous, then the supremum and infimum of f of I are both in f of I. Well, let's do it. Let's let I be a closed bounded interval, and f from I to R be continuous. So, flipping back if you need to, what does theorem 3.3.7 allow us to conclude? Damn it, these references are all wrong. I'm appealing to 3.3.7 twice. This plus one should be 3.3.5. What does 3.3.5 say? Ugh. I don't think I put, no, it is on the bottom. Does theorem 3.3.5 say?
I is compact.
I is compact. So, what does theorem 3.3.7 allow us to conclude?
F of K is compact.
Well, f of I is compact.
Oh, F of I,
So, by theorem 3.3.8,
The supremum of I exists in the elements of I.
almost the supremum of f of I is in f of I, and even better, though we didn't prove it, the infimum of f of I is in f of I. Oh wait, that's exactly what we needed. So, there's the proof of the extreme value theorem. As soon as you know a few things about how sequences behave on compact sets, it's automatic. And now, we could have done all of this proof just in the closed bounded interval I, and it would have worked out just fine. You would have taken like a sequence of elements in f of a comma b. That would have given you a sequence of elements in a comma b. But a comma b is bounded, so that has a convergent subsequence. The limit, pretty obviously, would also be in a comma b. And so you could appeal to continuity. But it turns out compact sets have an awful lot of super nice properties. If you like, compact sets are the correct analysis analog of finite. Compact sets somehow have only finitely much complexity to worry about. So a lot of arguments that have infinitely many things going on, you can boil it down to something finite. And if I had time to give you the correct definition of compactness, that would be clear. I don't. So, with that out of the way, I think that I want to get a start on the note packet that's actually in the schedule for today, the intermediate value theorem. And as I do that, maybe I'll even ask you guys first before you even plot over this note packet and see what the intermediate value theorem says. What does the intermediate value theorem say?
The continuous function on an interval from A to B, there must be a value between f of A and f of B, where there exists C between A and B such that f of C is between f of A and f of B.
It's getting close. So what it says is, no matter what value you pick between f of A and f of B, there's some input that hits that specific output.
Oh, yeah, okay.
The intermediate value theorem, abbreviated EVT, the extreme value theorem I will often abbreviate as EVT, the mean value theorem, which appears only in one of the optional projects, has you prove the mean value theorem, or MVT. Says this: if you have a continuous function on a closed bounded interval, and m is any number that's between f of A and f of B, I don't know which one's bigger. Maybe that even tells you something about how all the proofs will go today. Well, in this note packet, which I won't finish today, I'll assume without loss of generality that f of A is less than f of B. Like one of those two is true. There's some C in A comma B with f of C equal to n. And maybe you remember from your Calc 1 days, a chief use of the intermediate value theorem is proving that certain equations have solutions. And these are equations which aren't necessarily producible by any algebraic means. You have to use analysis to get them. So here's one. Well, this isn't. I'm going to change this a little bit to walk better with what I just said. let's prove that that polynomial equation, x to the fifth plus x plus 1 is equal to 0, has a solution in the interval from -10 to 10. And the reason I picked that polynomial, that I changed my mind from what it was, is because how many people are taking second semester algebra right now? Okay, well I guess most of my comments are just for you this semester. Galois proved, amongst other things, that this polynomial cannot be solved by any algebraic means. There's no formula for the solution to that polynomial in terms of any combination of roots, addition, subtraction, multiplication, and division. Well, cool then. Let's see that it does actually have solutions. So if we're going to use the intermediate value theorem to show that this thing has a solution, well, this seems like, well, we have an A and a B. We care that this output M is between f of A and f of B. So let's evaluate f of A and f of B. So let's let f of x be x to the fifth plus x plus 1. What's f of -10? I mean, it's negative, definitely. That sounds right. The point is that's less than 0. On the other hand, what's f of positive 10? It's 10,011. I feel like it's 10,011. I mean, the point of this class isn't can you do arithmetic. So 0 is between f of -10 and f of positive 10. So whenever m is any number that's between f of -10 and f of positive 10, there exists some c in -10, positive 10. So for some c in -10, positive 10, f of c is equal to 0 by the EVT. How do people feel about that? Here's another nice application. We've gone through a few times in this class and proved that there exists a square root of 2. Let's prove there exists a square root of 2. It'll take like 2 seconds. Let's show there exists a positive solution to x squared is equal to 2. What continuous function seems relevant here? X squared seems relevant. So let's let f of x be equal to x squared. Now I guess I haven't specified a domain. That's a function that's continuous everywhere now, so there's no constraint on what a comma b could possibly be so far. I'm looking for a positive solution though, so I'm looking for a solution that's bigger than 0. So what seems like a reasonable choice of a to try? Joel. I was going for 0, but. So let's see, f of 1 is what? Well, it's 1 squared, that's 1. How does that compare with 2? It's less than 2. What seems like a good choice of b to use? 2 seems like a good choice to use for b. And I'll be hopeful and think that that's enough space. What is f of 2? How does 2 compare with 4? 2 is less than 4. So, by the EVT, there exists some c in 0, comma 1. Nope, 1, comma 2. But you know what? The problem asks for an x, and I don't care what the EVT doesn't care that you call the output c. You can call it anything you want. There exists some x in 1, comma 2, such that f of x equals 2. In other words, x squared is equal to 2. So that was like, I mean, maybe you're going to say, well, we haven't proven the EVT, so maybe that's not actually an easier way to see that square roots exist. Depends on how hard the proof of the intermediate value theorem is. It won't be that hard. Yeah, let's do one better. Let's let m be any positive real number. Let's show that there exists a square root of that positive real number. So everything has a square root. Cool. So we're looking for a positive solution to, well, so just like the last one, let's let f of x be x squared. And I'm looking for a positive solution, and a positive solution over. That's the only thing that'll make me happy. So what seems like a good choice for A?
0.
0. And maybe we'll even just talk, wow, okay, cool. So let's see what happens at 0. So f of 0 is 0 squared, which is 0. Is that less than or equal to m? By assumption. On the other hand, I even give you a hint to think about m plus 1. So that'll be the choice of B. Let's see if m is less than f of m plus 1. On the other hand, f of m plus 1, what's f of m plus 1 equal to? M plus 1 squared. And like you have a pretty good idea of, like, you're going to FOIL this out, right? Of course you would FOIL this out. That's the same thing as m squared plus 2m plus 1. And my goal is f of b is bigger than big M. Can you tell me why that is bigger than big M? Let's see, m squared, is that positive or negative? Positive. Is 2m bigger than big M? It might be equal to it, m might be 0. But then 1 is positive also. So that looks like this is strictly bigger than m, since m squared is bigger than or equal to 0, 1 is bigger than 0, and 2m is bigger than or equal to m. Thus, f of 0 is less than or equal to m is less than or equal to f of m plus 1. So, there exists some x in 0, comma m plus 1 with x squared equal to m by the intermediate value. So the EVT is useful. It lets you solve equations.
You can generalize this to any power, right? You just have to effectively say, like, all the coefficients are, all the numbers involving n are positive since n is n, or 0 since n is not negative.
So if you guys have trouble proving theorem 3.5.5 on the homework, William can tell you the proof. I guess you're using like the binomial coefficients.
Yeah, that was my thought.
That seems like a good plan.
Okay.
So Lee and I have like a minute. That's not enough time to prove the EVT. So I'll give you a talk through of how the proof will go. So here's what I'll do. So I want to solve the equation f of x is equal to m on the nose. So here's how I'll think about it. I'll consider the set of all things where f of x is less than or equal to m. I'll prove that that set is non-empty and bounded above. I'll assume that I'm in that case. Then I'll think about the supremum of that set U. And I'll do two things regarding that supremum. I will prove, well, C is the supremum of U. I'll prove that f of C is less than or equal to m. And I will prove that f of C is bigger than or equal to m. And that'll do the job, won't it? Yeah. So, I don't have time to do it. The proof of the EVT isn't actually that hard. I bet you guys could go through this and then really understand Friday's lecture. I'm sorry that you all now have to waive that.
Yeah, this one's going down. Now I gotta go. Probably just gonna walk my bike if I want back.
I'll bike, I'm sure. Is there like what your message changes, what you learn?
Maybe I'll ask this. How many of you are giving a talk showing the macro tree? Have you already submitted an abstract and stuff? Okay, good.
So by the way, that 3.3.10 error, that was also on the previous page. That's why I think a lot of people were looking for theory 3.3.10 when it was referenced in the sheet.
Okay. There's something wrong in my type.
Yeah.
It's not my class type.
Oh yeah, no,
Scramble to get.
yeah. No, it seems like something that would definitely happen. Like if you read number of those items and
Or is your free whenever?
It's not to be that
Well,
thick. I've got it like duplicated. Because I'm using
That's exactly
Flash.
So
Oh, I should
we're the
stop
same,
recording.
and that's
Yeah,
all
so I
I have to coordinate.
have a pretty good